I do it as well. It feels nice.
Okay, it's a pleasure to have Parameswaran Nair from one of our neighboring institutions, City College, give a talk about young Mill's theory on CP2.
Thank you, Igor. Let me start by saying I'm not part of the collaboration, so let me congratulate Igor and the whole collaboration for this wonderful award. And also thank you for the time slot letting me talk here. What I'm going to talk about is about Yang-Mills theory on CP2. The topic is, I apologize, a little bit orthogonal to the tenor of the talks so far. What I would like to do is to construct or try to calculate the integration measure, the gauge invariant integration measure for a gauge theory in 4 dimensions. And the reason, of course, why I think that might be interesting is partly based a posteriori on the result we find. We find a result in the end, which has a 4-dimensional Weissenberger term, and there's a kind of a mass term. And this is perhaps interesting. It's definitely puzzling to us, maybe a bit intriguing. And it's also unclear what the impact of those terms would be. So what I'm hoping is that by presenting it here to this group of experts, we might be able to clarify some of the questions. Regarding credits, this is work I have done in collaboration with Dimitra Karabali and Antonina March, who is a graduate student. Okay, so let me say what this is about. The calculation is going to be modeled on what happens in 2 dimensions. So let me just very briefly run you through the 2-dimensional analysis. So in 2 dimensions, say if you're on R2 or on the complex plane, it's well known that we can parameterize the gauge fields like so. You take the complex components, write in terms of holomorphic derivative of a matrix times its inverse, and this is the complex conjugate. This matrix M belongs to the complexification of the gauge group. So if I'm looking at the gauge group SUN, M would belong to SLNC. Now, once we have this parameterization, one can write down a metric on the space of potentials, which is basically taking variations of this and integrating, and here would be the metric. In this language, in terms of M, it looks like so. And then you notice that there are these 2 N slots, which together would form SLNC Cartan metric. Therefore, from here, we can read off the volume element in the following way, that you would get the determinant of this DD bar matrix here, the operator here, the measure, R measure on SLNC, of course, over all the points in space. And this splits very nicely into the gauge part, the unitary part, the Hermitian part, which is on this course at SLNC mod SUN, and the determinant coming from the D bar D gives you the Weissenberger in action. So at the end of the day, then it's easy to just drop this term regarding the gauge part of the degrees of freedom you have, and one gets a measure which is on the gauge invariant space. So this calculation is well known. It goes back 30 years plus to the work of Gavetsky and Cobain. I mentioned the 2-dimensional plane, but you can also do this on the sphere or on the complex projective plane, projective line. SU2 mod U1. I mentioned this because this is the structure we're going to find later. We can use an element of the group SU2 to coordinatize the space with, of course, the identification that G and GH, where H is in U1, correspond to the same point. A similar parameterization to what I showed you in the previous page, namely this, can be done where R plus and R minus are translations on CP1, realized, if you like, as the right group translations on the group element, which coordinatizes the space. The question we want to ask here is, can one do something similar in 4 dimensions? And if we can, what are the kind of features that would emerge, what would be interesting? So the space we would like to look at is CP2. We think that is a rather reasonable space to look at. 4 dimensions, it has a complex structure. I can write this a group coset SU3 mod U2. So many things we can construct using group theory methods. The Fubini study metric, which is the standard metric on CP2, has this form in terms of local coordinates C and Z bar. There is a parameter R square, which I can take very large so that it starts looking a bit like flat space. Some sort of comparison perhaps would be possible. Okay. Of course, CP2 has reduced isometries compared to the flat space would be interested in. But it's also true that CP2, if I mod by a certain conjugation symmetry, that's a 4-dimensional sphere. So maybe it's not too far from a more isotropic situation. This is a hope that this space might be a good candidate to look at for this sort of calculation. Okay. Now, what I'm going to do, I had to show you a few fairly technical slides. Therefore, I just want to tell you initially what I plan to do. I will talk about parameterization of functions, vectors, and gauge fields on CP2. I will write down the metric and the volume element. I'll talk a little bit about propagators and then tell you the result that I alluded to in the beginning. Okay.
Is it possible to add fermions and CP2
right, that's right. There's no spin structure. We are not looking at fermions so far, so we didn't worry too much about it. But perhaps with a spin C structure, one would do something, actually. Right? It does admit a spin C structure, right? So, but we haven't come to that point so far. Okay, so let me talk about CP2. We're going to use a group element, SU3 element, to coordinatize the space. The fundamental representation of SU3 given by a 3x3 unitary matrix G. I just have to establish some notation here. Right translations can be defined like so. Operators acting on G, put a T matrix on the right. T is half of the standard Gell-Mann matrices that we use for SU3. Of these 8 matrices here, the ones correspond to 1, 2, 3 will define SU2, which I will colloquially refer to as isospin, because that's what we all learned to call it when we learn hadronic physics. T8 is the hypercharged direction U1, and these two together form the U2 that is quotiented out from SU3 to get to CP2. The remaining directions combined into complex directions, they are the complex directions of CP2. So we can take these R operators, combine them along these lines, R4 plus Ri, R5, and so on, call it Ri and R sub I bar. I and I bar correspond, take values 1, 2, they define translations on the space. Okay, so that's just basically setting up the structure on CP2. What are functions on CP2? They have to be invariant under the U2 that we are quotienting out. So we can define functions in a convenient way by looking at representations of the group element G in an arbitrary representation. Take a more decomposition like so for functions with arbitrary coefficients, these functions here. What we need to ensure here is that right translations on G, if I look at these ones, T1, T2, T3, and T8, which correspond to the U2, which I'm quotienting out, then this state on the right should be invariant under that. Okay, that invariance will guarantee these are functions on the space. Okay. So functions would admit a more decomposition like so. And these, of course, are the representatives of G. They are sometimes referred to as Wigner matrices. They are finite dimensional unitary representations. And as I just mentioned a moment ago, if I look at the 1, 2, 3, 8 directions, the state on the right side here in this mode decomposition for functions is invariant. Therefore, this result holds. Okay. Now, if we label the SU3 representations in the conventional way as obtained by a product of a number of fundamentals and anti-fundamentals in the kind of the tensor notation that we are familiar with, then if I call them P comma Q, namely P upper indices, Q lower indices, then this particular state I'm talking about, all the values assigned to these labels are 3, so they are SU2 invariant. This is the equal number of P's and Q's, so it's a PP type representation. Okay, that's what we need to construct the functions. But what we are interested in is also to look at vectors. Vectors are SU2 doublets. They should also carry hypercharge, the TA charge plus or minus 1, basically because the R that I mentioned here, coming from here, carry hypercharge plus or minus 1. So there are two ways to get this. We can look at functions and take derivatives. That'll be one set of vectors that we can get. But there are also other representations of SU3 or the P plus 3P type. So P's and Q are not identical here, or PP plus 3 type, they contain vectors as well. Okay, those are the only representations which can produce vectors for you. Therefore, one can actually write down a complete mode expansion for vectors as well. Okay, and indeed, if I take a look at how the vectors look like, there is a derivative of a function, and then there is a mode expansion I can write like this. This index I means it's a doublet. I have to pick the appropriate state on the right side, but the remaining entries are all 3, which means SU2 singlets. Okay, so if I look at this particular state here, I realize that I can also write it as an R bar derivative on an SU2 invariant state, but this state will have hypercharge equal to 2. It's lowered by 1 unit because of the R bar, which giving us the hypercharge plus 1 that we need. Okay, so because I can write it like this, I realize that this parameterization can be simplified to look like this. So there is a gradient of a function, and then there is essentially this quantity here, R bar going with AI and R going with A bar. And if I take this group theoretic formulae and translate them to standard world coordinate notation, this is what you find. These are the, this is the parameterization. Okay. At the end of the day, you realize that this is not very surprising. Chi's here are antisymmetric tensors. They are proportional to epsilon. And then you realize this is very much like the Hodge decomposition. Okay. The important thing is that because we went through the group theory argument, we know that this is a complete parameterization I can use. Okay. Now, how do I generalize this to the non-abelian case? I take this, I notice that these are gradients. They're like what we do for gauge transformations for gauge fields. It's complex in the present case, of course, but even so, we can integrate this up, so to speak, and write a non-abelian generalization like so. Okay. Once again, M and M dagger are SLNC matrices. If I take gauge group SUN, here is a gauge covariant term here. They should transform covariantly, but it goes like so with the R bar or the D bar, it goes like a covariant derivative bar. Okay. So these two fields phi and phi dagger are the additional things that we need. Now, of course, the derivative here is simply defined with the connection coming from M, basically because we cannot use AI on the right. Everything has to be written in terms of these fields. Okay, so this is a good parameterization for non-abelian gauge fields on CP2. We can write it in a slightly different way, which will become useful later. Instead of writing in terms of this phi's that I showed you here, I can also write it in this fashion, which looks a little nicer, if you like, in this way. The important thing is that the gauge transformations act as left translations on M. Therefore, AI are gauge invariant degrees of freedom as well. Okay. Now, this parameterization, I gave you the argument to get to how we can get to this this parameterization. But notice also that if I drop this A and A bar, then these are just gradients, and therefore the 0,2 component and the 2,0 components of the field strength tensor for the curvature would be 0. So in fact, this parameterization can be used for anti-Servedal instantomes, and in fact, it has been used in that context as well. Okay, so from this thing, we read off the gauge invariant degrees of freedom. M dagger M is one of them, that's 1 degree of freedom. Then there is a combination of the phi that I showed you and M, which is gauge invariant, and its conjugate. So these are the 3 gauge invariant degrees of freedom that we would have, in addition, of course, to the pure gauge degrees of freedom. Okay, so what do we do now? We take these expressions and simply take the variations of this and write down a metric that we want to calculate. So here is a formula for the metric. It's a little messy, but it's not conceptually complicated. Just take variations, put this in here, and you notice that it has the structure of some matrix M, which I call script M here, with these differentials on the left and right. This involves variation of M. Theta dagger is variation of M dagger, and similarly for phi's also. Okay. Notice that here is a matrix between theta dagger and theta. Similarly here, there are more complicated terms here. Okay. If I look at this metric that I wrote down on the space of potentials, if you like, and let me also define another metric, which is without this matrix M in the middle, like so, then you can see that this structure is very similar to what we had in 2 dimensions. If I take the volume element corresponding to this, that'll be related to the volume element corresponding to this via an additional Jacobian matrix coming from M. Okay. Therefore, one can actually write down a formula for this and calculate. Okay. So here is in the equations, just what I told you, square root of the determinant of M. And the important point is that this one again, because of the structure of these guys here, we realize that one of the components of that is just the Cartan metric, SLNC Cartan metric, and therefore it's easy to factorize the gauge degrees of freedom. The volume element factorizes in this fashion. This is the gauge degrees of freedom. This involves the gauge invariant combination M dagger M. These are also gauge invariant degrees of freedom. And then I have the Jacobian matrix here. Okay. So it's therefore possible to reduce the computation of the gauge invariant measure of integration to this formula here, where of course I now have to calculate this Jacobian matrix. Okay. Sorry. I need this line also here. Okay, so how do I do that? Well, computing a determinant is something that we are familiar with. We just write it in terms of an action, introduce some bosonic degrees of freedom just as an ad hoc thing that we need to calculate, write it in the form of an action. Functional integration gives you the determinant. So I'm going to use this to calculate. Okay. So there is a 0th order term, if you like, which is involving two scalar fields. This corresponds to the fact that we had certain functions, M and M dagger, when we started. And then there is also a y equal to 2n minus 2 field coming here. And then there are many terms which are kind of interaction type terms in this language. Okay, so the strategy we're going to use is simply take this way of writing the determinant, use familiar Feynman diagram techniques, and calculate this. Okay. Of course, when you do the calculation, we have to know the propagators to do the calculations, because we're going to do Feynman diagram type things, and those can be calculated. Because CP2 is such a nice space, defined as a group coset, we can use a combination of some solving the differential equations and use some of the group theory to fix some terms, and you can exactly calculate the free propagators for the fields that we need. Okay, so for the scalar fields, here is how it looks, and here is for the y equal to minus 2 field, which is the other one that we need. You recall that here we have those two fields coming here as sort of the free part of the action, so to speak. So we have to calculate propagators arising from here. Okay. So we do this, and this parameter S is simply a definition of an invariant way to define distance on the CP2 manifold. In terms of the homogeneous coordinates of CP2, here is the expression for this square of the distance that one can write down. We also need an ultraviolet regularization. And what we do is a point splitting regularization, which we can do again in a way that preserves all the isometries of the theory. What we do is to shift the point, you take the distance, shift the point y to another point y prime, which is related to y in this fashion. Alpha is a small number of the order of square root of epsilon in magnitude. We do an angular average over the face of it as well. In the expressions for the propagators I showed you, there is a phase factor here for the y equals -2, and we have to do a shift there as well. Okay, so this provides us with a point splitting technique that is consistent with all the isometries of CP2. Of course, we also need to preserve the gauge symmetry, so there's an extra Wilson line needed, which we construct in a similar way, okay, by a small shift between these 2 points. Okay, so at the end of the day, what we are saying is that we have an ultraviolet regularization that's both gauge invariant and consistent with all the isometries of the space. So we can use that to actually calculate this determinant. Okay. So we do that. That's the long part of the calculation. And I'll just tell you what the result is. So the integration measure, which I displayed to you like so initially, I'm going to write the Jacobian as e to the gamma. Here is the expression. So we calculate gamma. There's a term gamma 0, which is the integral of a dimension 2 object. There is another one, gamma 1, dimension 2 object, but this is quadratically divergent. Okay, 1 over epsilon, epsilon goes to 0. This term is actually finite. There is a log divergence as you expect. And then, of course, there are higher terms which are finite. Okay. So the first thing we realize, not a big surprise again, is that if you want to define the measure properly, you had to renormalize the measure. You have to have a renormalization procedure for the measure. Okay, so that's what we will talk about. We have to get rid of these terms here. And I'm going to discuss each of these terms, but I will do it in the reverse order, starting with gamma 2 and coming down to gamma 0. So what do we find? Well, gamma 2, there is no big surprise again. It's log divergent. A bunch of terms involving the fields I showed you. H was that field M dagger M, which was gauge invariant. And remember that there was a little a that I put for the second part of the gauge potentials. So it's a combination of things. This is not quite F squared. Some of the terms like this, for example, can be seen to be in F squared, but there are other terms here as well. So it's not exactly what you would expect in flat space. But again, that is not particularly concerning because we are, after all, looking at a space with less symmetry than flat space. Therefore, more tensor structures are allowed. And therefore, this is the kind of thing that we might expect. So what do we do with this? Well, clearly one has to renormalize, eliminate this divergence. And after renormalization, there should be a finite coefficient here. Okay. How do we fix the coefficients? That is still a bit of a puzzle to us. In usual perturbation theory, if you compare with similar questions there, remember, defining the measure in the usual perturbation theory, that has to do with the ghost sector of the theory. There, of course, there are renormalization constants, but you can fix it by BRST invariance and then using some normalization conditions. Okay. What would be the analog of that here? That's not entirely clear to us, actually. Okay. But it should be possible. Yeah. Okay. Second, and this is an even more puzzling term here, which I think is sorry, I showed you. So I mentioned to you there are several terms here, and now I'm going to look at this quadratically divergent term here. And that one has this structure. It's quadratically divergent, as you can see. But what comes here is little a bar, h, little a, h inverse. And let me remind you, little a and little a bar appeared in the parameterization of the fields like so. So there's a gauge invariant degrees of freedom. And this is like a mass term for these so-called transverse degrees of freedom here. These are longitudinal. And that is indeed kind of interesting. This is completely consistent with the isometries of the space. Fully gauge invariant, completely consistent with isometries. In that sense, it's a little bit difficult to dismiss. I'm going to just throw it out. Right? Now, of course, once again, you would expect that this has to be renormalized. If you renormalize, there will be some finite parameter multiplying this in place of this divergent coefficient. And in this, we think, is really what dimensional transmutation is in our language, actually. Normally, we find it in terms of computing, running at the coupling constant, things of that sort. But if you're setting up the theory in terms of an invariant functional integration measure, this is probably the place where it would enter. How would we check that? Well, one possibility is, after all, I have done nothing here that is different from what we normally do, except that I have a different parameterization of fields. So one could recalculate coupling constant renormalization in this framework and check that lambda QCD is somehow related to this parameter. That is the thing that we are trying to do now. And I think that is doable. That should be possible. Okay. The last term, this is the term I told you is integral of a dimension 2 object. And it is in fact the Weismann-Witten action for this field H. Looks like that. Omega is the Kähler form for CP2. So this is the usual Weismann-Witten in 1+1 upgraded to 4-dimensional space. So this is the 4-dimensional Weismann-Witten theory. The coefficient here, because this is a dimension 2 operator here, you would expect just on dimensional grounds that it can come with a quadratic divergence. But here is where we find a big surprise. All the divergences cancel out. This coefficient here is actually finite. So yeah, that's good. So we don't quite know why, what to make of it, but it is definitely an intriguing result. We can in fact calculate the coefficient exactly. This is for CP2. We try to do this also with an infrared cutoff because in this expression, recall, there are these terms which I didn't calculate and show you. So if you want to argue that these terms are small, one may want to impose some sort of an infrared cutoff, which also brings it closer to comparing with flat space. So just wanted to double check that. So we did that, and we find that that still remains finite, and it is proportional to the cutoff that we impose. Okay, so this is the key result that we have. And what does it really mean? We are trying to interpret this, and here is one possibility. I showed you this term, which looks like a mass term. If I look at energy scales much below m square, then presumably these transverse modes do not get excited. And then what we have then is essentially the measure reduces to just this Weismann-Witten theory. Okay, it's a Hermitian matrix, Weismann-Witten theory, finite coefficient here, and that is really kind of intriguing and interesting. Okay. This, of course, 4-dimensional Weismann-Witten theory, there are many nice features, and it has a long history, many interesting features. It appeared first in the work of Donaldson. Jeremy Schiff and I looked at it many, many years ago. There are many other papers, including recent paper by Costello and so on. Two features I just want to point out. The extrema of this WCW action, they are anti-subdual instantons. And there is a chiral factorization via the Polyakov-Wigman identity. So there is a chiral algebra that splits into the two holomorphic and anti-holomorphic sectors. So the key, just to summarize, so the key takeaway point is we have a parameterization of the gauge fields, which allow us to formulate the calculation of the integration measure in a manifestly gauge invariant way. What I call the mass term, that is one of the terms that we find, and then the Weizmann-Witten term. These are the leading terms in this result. It's a bit of a surprise that Weizmann-Witten term has a finite coefficient, and there's a possibility that that would dominate the theory at energy scales much lower than it. So what is the reading of this for four-dimensional Yang-Mills theory? What are the conclusions one can draw? I can't really tell you because we are still trying to understand that, and that's what I hope some discussion can help. Okay, thank you very much.
Much for an interesting talk. Questions?
Yeah,
So the relation between these gauge invariant operators and the more standard ones, like traces of products of FP,
will be highly non-local.
non-local,
Highly
for
non-local.
all of them, or
For all of them.
Okay.
Yeah. In principle, one can painfully convert it to the usual one, but
So you did this for D equals 3
yes,
intensively, but simpler,
yes,
and you actually tried to do the goal of this collaboration. In D equals
Wow.
3. Could you
Equals
just
3.
update us on the status of that? Briefly?
Yeah, in D equal to 3, what we did was very similar. But because it's 2 plus 1, the framework was a Hamiltonian framework. So we tried to solve the Schrödinger equation. We found the ground state wave function. And from there, because the time slice is 2D, we could exactly calculate the Wilson line from there. Exactly, I mean, in the sense of for low momentum modes. Okay. So large Wilson lines, we thought we could calculate. We found an answer for the string tension, which seems to agree with lattice data to within 2% or so. This is the work. Most of the lattice data comes from Mike Tepper's work. Later on, we tried to see what kind of corrections you might get to that. That is a long, hard slog. But at the end of the day, we did calculate the corrections, and we found something rather strange there as well. The corrections were extremely small. Okay, whereas a priori, there was no reason to expect it should be, because there was very little parametric control over that. But it so turned out that the integrals involved in the corrections were just numerically very small. But there were some cases of big cancellations happening. So we feel that that was kind of a framework we developed, which probably is far from ideal, that somehow if we could combine several terms that all the cancellations would be obvious, and it would be much clearer. Okay. But the interesting thing was that the corrections we found shifted our answer closer to the lattice answer, actually. So that was encouraging, but we're not sure what more one can do there.
What is the expansion parameter for those corrections?
The 2 plus 1 case?
Yes.
Yeah, there was a, okay. So what happens is that these integrals come with certain powers of something that looks like k squared plus m squared in the denominator. Okay, and then you integrate over k. The number of powers of that denominator keeps on increasing. That is kind of so it's not really a clear-cut parameter in the theory, but numerically they tend to go down and down as you go. That's what happened actually. So
is that a bit like strong coupling?
it's a bit like that, yeah. But the fact that one could actually set up a framework for corrections and calculate them and see that they were small, which is quite nice. But I always felt that the smallness of the corrections, there must be an explanation, and I hadn't found it yet.
In the spirit of this collaboration, should one go back and there were some other problems with that, I remember. It's been 10 years.
Yes.
Not 50, but 10.
maybe 15.
Well, there were several papers over a few years, so.
Right. But you're not telling us that it's,
I'm sorry.
you still think it's promising. That could.
I think it's promising, but I'm fully aware that there are questions because there was no obvious clear expansion primed. Okay, but on the other hand, I think it is still promising because I mean, everything we did on that problem seemed to give something closer to what we expect. And one more thing I want to say, 2 years ago, we looked at the problem on a different way. There was a lattice simulation of Casimir energy for the non-abelian gauge theory. And they found a curve for the energy as a function of the separation, essentially the standard two parallel plate scenario. And what we found was that we could simply take our formula, calculate that the profile of that, and that fit with no parameter other than what we had before, just a coupling constant. It fit to better than 1%, actually. And that, again, it's quite a bit of a surprise, actually. So given that, we feel that there is something in that, that strategy, but there are clearly more things to be understood there.
Any more questions?
So when the CP2 is very small compared to the QCD scale, then the theory should just be weakly coupled, and then it should all be perturbative, right? So you expect that this mass parameter will sort of interpolate between 1/r and that
I think that is probably what will happen. Yes, exactly.
And can you try to compare it with perturbation theory in this limit where the radius is very small?
Well, that's what I was mentioning, that we are trying to do the perturbation theory part to see how the comparison goes. And this is just very recent, so we didn't have time to finish that.
Okay, well, thanks a lot.
Thank you.